Hello everyone, I am Thibault Louis and today I'm going to discuss our new measurement of CMB polarization from the Atacama Cosmology Telescope. And the talk will be done in two parts, so I'm taking care of the first part and then Colin Hill is going to take care of the second part. But let's start in the Atacama Desert in Chile. This is a drone footage of the site, so you can see the site here, and this is where the Atacama Cosmology Telescope resides. So you can see that it's within a ground shield to protect it against ground emission from the surrounding. So this is a picture or video from above, and actually the site changed quite drastically since this video was taken. Okay, so this is the most interesting part of our telescope, but one of the most is the fact that we have a very large mirror. So this is the primary mirror, and its diameter is around 6 meters. This is our secondary mirror, so the way it works is that the light goes through the primary mirror, then the secondary mirror, and then to the receiver. And of course, when we are taking cosmological observation, usually people are not standing on the telescope. And finally, this is the receiver, this is where we have our detectors. Okay, so the ACT detectors array, we have 3 of them that we call PA4, PA5, and PA6. PA4 observe at 150 and 220 GHz, while PA5 and PA6 observe at 90 GHz and 150 GHz. In total, we have around 3,750 working detectors at 100 millikelvin. So this gives us a combined sensitivity of 6.2 μ/s and also an angular resolution of 1.4 arcminute. And just to give you some context, this is 4 times the angular resolution of the Planck satellite. So this is us. In ACT, we have around 160 collaborators. You can also see our sponsor, and we are particularly grateful to the NSF for their support and to the Ministry of Education of Chile. So today I'm going to talk about our latest data release with 3 main papers. A paper that describes the map, a paper that describes the power spectral likelihood on Lambda-CDM parameters, and a paper that describes extended cosmological model. And this part will be covered by Colin Hill. Alongside the paper, we release all the data products that are needed to reproduce our analysis. And for the first time in CMB data analysis, we not only release the data, but we also release the entire analysis pipeline that allow us to produce our results. So you are able to rerun our analysis pipeline and to reproduce essentially all the figures of the power spectrum paper. So by doing so, we try to follow the footsteps from Planck, which was very public. So they released their likelihood, their map. They also did this partial release of their analysis code. And in ACT, we just go one step beyond that. We are doing a full release of our analysis code. So you can see that this is also in contrast with other ground-based experiments today. So why do we believe this is important? Well, since we are approaching percent level on constraint on parameter, we are seeing all these signs of tension or hint of new physics that are emerging. One of the most famous one is the H0 tension, the 5 sigma tension between the truth measurement and the Planck measurement of H0. We have the Planck anomaly with this 3 sigma-ish amplitude of lensing of Planck, which lead you to a detection of curvature. We don't believe that this is the actual result, because once you combine the Planck data with low redshift data or even with its own lensing measurement, this goes away. So this is really an anomaly from the primary CMB determination. And we have the deg equation of state of dark energy. So this is a very recent result that we now have evidence for possibly evolving dark energy. So given the state of the art of in cosmology, where we have a lot of measurements and some of them disagree with each other, we are not sure of which new physics is solving all of them, we believe that the only way to make progress is to strive for maximum transparency and reproducibility. So this is why we put our data on Lambda. So if you go on Lambda and you go in this ACT 6.02, you will get our latest data release. And if you want to look at the code, you can just go on GitHub, and in the Simons Observatory GitHub, you will find PS pipe with the code that allow you to reproduce our analysis. We have also adopted a blinding strategy to protect us against our confirmation bias, and we have documented in the paper every post-unblinding changes. Okay, so this is just for the method, but let's look at the actual result. And before we go to the ACT result, let me remind you of this beautiful measurement from the Planck collaboration. So this is a map of temperature anisotropy taken by Planck. And what's fantastic about this map is that at this zoom level, every single thing you are seeing is a real feature on the sky. Basically, you are not able to see the noise in this map at this zoom level. If you want to start to see some defect or some, residual instrumental thing in this map, you need to zoom quite a lot. And this is what I'm doing here. I'm zooming on the 13 times 7 degree patches, and we are looking at the Planck data here. And let me show you the effect of the addition of ACT into Planck. So you can see that, Planck does erase some of the small scale noise that there is at this zoom level on the Planck map. And another thing that ACT does is that it reveals some substructure in the map. Here you can see this very bright point here. So this is not CMB. This is actually a contamination to the map from extragalactic sources. Some sources are nearby galaxies, like this one, that we can actually resolve in an elliptical galaxy. And some of them are very far away and we cannot resolve them. They are just like point source in our map. You can also see a cluster of galaxies here as a blue point. So the angular resolution of ACT actually allows us to reveal this structure, so then we can of course study them. But if our main goal is to do like cosmology from the cosmic microwave background, seeing them also allows us to mask them, so to remove them, then mitigating their contamination to the cosmological results. So it's actually useful to be able to see them and to have this angular resolution, even just for doing the cosmology. But where our measurement is the most impressive is in polarization. So on the right here, you see the Planck measurement of E mode on the top and B mode at the bottom. And on the left, you see the effect of adding the ACT data on the top of the Planck data. And you can really see that the ACT data reveals a signal-dominated version of the polarization field in E mode of the cosmic microwave background. And for the first time, this is done over a very large portion of the sky. By signal dominated, I mean that if you were to remake a measurement of the CMB polarization in 1000 years, you will see the features that you are looking at here. Of course, what you can also see here is that there is more E mode on the sky than B mode, and this is a prediction from the the standard Lambda-CDM model that we are dominated by this E mode, and here you can see it in map space. You can also see some very bright features here, and this is actually an extragalactic sources seen in polarization. So yeah, this is the main achievement of ACT, is to really have revealed this E mode map of CMB polarization over a large fraction of the sky. So let's look now at the statistical property of this map. But before I show you the result, let me point you to some facts. First, let's look at the noise power spectrum. So in dark blue here, what you are looking at is the Planck noise power spectrum. And this curve has an important meaning because in particular when you compare it with the signal power spectrum. So the signal power spectrum for E mode is this gray curve here. When the dark blue curve is above the signal power spectrum, it means that we are noise dominated. And you can see that this happens around a multiple around like 600 to 700 for Planck. In ACT, we get this noise power spectrum here in red, which is below. It means that we are signal dominated over a much wider range of scale. And this is why we were able to produce this beautiful map measurement, because every angular scale that is basically bigger than 0.1 degree, corresponding to this multiple here, is signal dominated. We are able to really make a map of it. You can also see that the different detectors wafers that we have in ACT, so I mentioned PA5, PA6, and the different frequency. The different measurements are also quite close together, and it's only when you combine them that you get the red curve. But the fact that they are quite close together means that you can do very stringent tests on the data. You can compare the signal seen by the detector here represented in blue, and the one in orange, and the one in purple, and the one in yellow. So having this redundancy in our measurement of the polarization was very useful to test the data. So before unblinding, we have performed around like 2000 tests of the data. We check that the results do not depend on array band, weather conditions, scan elevation, sky location, time of observation, and even the position of the detectors in the focal plane. So this is one of the examples of the test that we did here, where we are comparing, for example, the 90 × 90 power spectra with 90 × 150 for the E mode, and we expect this to be 0 once we take into account the foreground contamination, which is done here, and indeed the residual is consistent with 0. Okay, so now let's look at the actual signal power spectrum. So just a reminder of the measurement from Planck, the temperature power spectrum from Planck, and now the addition of the ACT temperature power spectrum on the top of it. So you can see that the ACT data extend Planck measurement to small angular scale, that they are very constant with Planck data on overlapping angular scale, and that the ACT plus Planck data are fitted by a common model. But where our main result reside is in this measurement of the E mode power spectrum. So again, I'm starting with the Planck measurement, and now I'm adding the ACT measurement on top of it. So you can see that the ACT E mode power spectrum is actually more sensitive than the Planck E mode power spectrum, starting at multipole L equals 600. So you can see that they are basically the blue point here, and you can see how sensitive the experiment is to measure the small scale polarization. They are corresponding to all the blue points here. And finally, the TE power spectrum, so the correlation between temperature and E mode anisotropy. Again, in orange, this is the Planck data, and in blue, this is the ACT data. So this observable is actually quite useful because there is not a lot of foreground that contaminate the TE power spectrum, meaning that if you can do cosmology just from this observable, you are a bit less concerned about potential foreground contamination that will contaminate your cosmological results. And for example, just using this combined TE power spectrum, we are able to set a 1.1% constraint on H0. And given all the controversies that exist on the measurement of H0, having very clean measurement of the Hubble constant is something very useful, and that's something we were able to do with our combined TE power spectrum. So what about B modes? Because the main power spectrum that you are going to use to do cosmological parameter estimation, the standard cosmological model, are TT, TE, and EE. But we have also a prediction for what the B mode should look like. So let me show it to you here. So first, here in EE, I'm showing you the EE power spectrum in black. And to show you the B mode, I will have to zoom quite a lot on this curve. And this is what this animation does. We are zooming on the E mode power spectrum and to show you how small the B mode is with respect to the E mode. And basically, the prediction, the Lambda-CDM prediction for what the B mode is this dash gray curve here. So you can see that it's a very, very small fraction, less than 1% of the E mode power spectrum. And yet, collectively, with our colleague from BICEP in red, SPT-Pol in yellow, and Polar Bear in green, we are already able to set constraints and to measure this B mode power spectrum. So it's not the most exciting B mode, which would be like primordial gravitational wave generated by inflation. This is only the B mode that results from the landing of E mode. Yet it's kind of unbelievable that we are already, at the precision where we can measure this, combining all of these different experiments, and that our measurements agree with the prediction from the Lambda-CDM model. I think this gives us a lot of trust in the story that we are building with our other results, that we also have a consistent story when we are including our B mode measurement. It's also a good test of instrumental systematic. Given how small and sensitive B mode measurement need to be, the fact that we recover a result that is consistent with our temperature and E mode power spectrum measurement gives us a lot of confidence in our handling of the systematic effect. So what about parity breaking spectra? So no TB and EB power spectra. Again, in Lambda-CDM, we have a prediction for this. They are supposed to be 0. And this is because there is no parity breaking mechanism in the universe at first order. So basically, under an operation of parity, EB is equal to minus EB. And the only way this can happen is if EB is equal to 0. So the prediction from Lambda-CDM for the EB power spectrum is this dash black line here. And here you can see that actually the data prefers something different. And this is shown here by this probability to exceed. A model, the dash black line model, has a PTE which is really, really disfavored. It's greater than 5 sigma. So why are we not making a big deal out of it? You know, we have this very clear detection of a parity breaking mechanism in the universe if you just look at this spectrum. Well, there are two different reasons why we don't make a very big deal of it. The first thing is that there is some degree of disagreement on our measurement of this EV power spectrum for different detector wafer. So we parameterize the EV power spectrum with a single angle here, and you can see that there is some mismatch for the angles that we are getting for different detectors wafer. The other thing that prevents us to make a big deal of it is the fact that once we include all the systematic errors that we have in our measurement, it decreases the significance of this detection for a non-zero EB power spectrum. And this is because the EB power spectrum is fully degenerated with our determination of our polarization angle from our instrument. Do we know exactly what is the polarization angle measured by our detector's wafer? If we don't know perfectly, then it's going to increase the uncertainty on our ability to do physics from the EB power spectrum. So once we combine both the statistical error and the systematic error, we have this measurement for our deviation with respect to 0, and you see that this is less than a 3 sigma detection. And this explains why we did not make a big deal of it. We have this hint from statistical error only of non-zero birefringence or non-zero angle in our data, but once we propagate systematic error, this evidence decreases. Okay, so let's go now to the main result, which is a Lambda-CDM parameter measurement. This is what we got with ACT. And here you see the comparison with the Planck cosmological parameter result in orange. So you see that there is a very nice overlap for the different posterior on the different cosmological parameter. You can see even that for NS we get exactly the same value as Planck. And we did this statistical test to check if ACT cosmology and Planck cosmology agree, and we get that they are consistent at the 1.6 sigma level. So this is a really important result, this agreement between the ACT measurement and the Planck measurement, two very different experiments that also measure very different scale, yet they get the same cosmological constraint in Lambda-CDM. Since both experiments are telling us the same story, this motivated the creation of a combined dataset that we called P-ACT for Planck plus ACT, and this dataset lead to state-of-the-art constraint on cosmological model. So this corresponds to the gray line here. You can see the Planck data in orange and the ACT data in blue, and then the residual. So basically when you subtract the model from the data, you expect if the model is a good model, you expect that this looks basically like 0 with a normal scatter, and you can see that this is the case in temperature, in E modes, and in the correlation between temperature and E modes. So basically we have a very good model that fits both ACT and Planck, and this model is Lambda-CDM. Just to show you how complementary the different datasets are, so here in light blue you have the ACT constraint on omega b on NS, and in orange you have the Planck constraint, so you can see that they have actually different degeneracy direction, and this is because we are measuring again different angular scale, and when you combine them you get the dark blue constraints that benefit from both worlds. And now let me introduce Colin Hill for the Beyond Lambda-CDM investigation.
Okay, great. So thanks, Thibaut. I'm Colin Hill from Columbia. I'm going to pick up from where Thibaut left off to tell you about some of our new cosmological results from ACT-DR6. And this is work that was done by the whole collaboration, and I highlight some of the key players in the Beyond Lambda-CDM and Lambda-CDM work down here at the bottom. Okay, good. So the cosmological results are contained in these two papers. Before I dive into those, I just want to quickly remind you about the inference framework in which we're working here. So in particular, note that in these beautiful maps that Thibaut showed you, the CMB is not the only astrophysical signal that we observe. So if we look here at the TT power spectrum measured from the different combinations of frequency bands that we have in ACT-DR6, what you can see is that at intermediate scales here, the different frequency bands see the same signal, and in the units that we work in, the CMB is constant as a function of frequency. So this is telling you that it's CMB dominated here, but out here on very small angular scales, you can see that the different frequency bands see a very strongly frequency-dependent power spectrum, and that's telling you that there are non-black body components, foregrounds that are out here, which we need to model in order to extract robust, unbiased cosmological constraints from the underlying CMB component. So I'm not going to go through that process in excruciating detail, although it's very dear to my heart, and just summarize it here on one slide. So the model that we develop in the TT power spectrum comprises 10 free parameters, fitting components like the cosmic infrared background, the thermal Z power spectrum, etc., all of which are very rich science cases on their own. And then in polarization, it's a much simpler model with just 2 free parameters in TE and EE for polarized galactic dust and polarized radio point sources. One thing I'll highlight briefly before proceeding is that we do introduce some new aspects to this modeling beyond previous work. So in particular with DR6, we're now sensitive to the shape of the thermal Z power spectrum and not just its overall amplitude. And we detect a parameter characterizing that shape at 3 sigma. There's a new paper that'll appear on the archive between when I'm recording this talk and when you watch it that dives into all the details about the foreground modeling. So I encourage you to check that out. Okay, so before looking at beyond Lambda-CDM, an important cross-check that we want to first do is to look at the Lambda-CDM fit to what we call p-act, so Planck plus act, as Thibault introduced, and then see if that prediction from the primary CMB actually agrees with what's measured directly at low redshifts. So I showed 2 examples of that on this slide. So on the left here is the CMB lensing power spectrum, so from the 4-point function of the CMB. The orange and the dark blue dashed curves are the predictions from either Planck or p-act, and then the points are the actual measurements from ACT DR6 lensing or Planck lensing. And you can see that the prediction goes very nicely through the points, which is, I think, a remarkable end-to-end test of the cosmological model. The right shows a very similar exercise for the BAO distance redshift relation. The black points here are DESI DR1. At the end of the talk, I'll quickly show you some DESI DR2 results. But again, the PTE for p-act in particular is quite acceptable, so we don't see any obvious failure here that Lambda-CDM doesn't fit the data acceptably well. So we can then proceed to combine these data sets, and that's what we do to form the data set combination called p-act LB. So L stands for CMB lensing, B stands for DESI DR1 BAO. And that combination gives state-of-the-art constraints on cosmological parameters. So the dark purple here is the p-act LB combination in Lambda-CDM. So for example, if you're interested in H0, this gives a 0.5% constraint on the value of H0 in Lambda-CDM at 68.2 plus or minus 0.36. And if you have friends who maybe don't believe in dark matter, you should remind them that we detect the existence of a non-baryonic but gravitationally clustered component of matter at 130 sigma with this particular analysis. All right, so then let's start to look at some extensions. So the first extension you might look at is what's called a lens. So this is just a parameter that characterizes how much peak smearing or gravitational lensing is imprinted on the CMB power spectra. So this is not from the 4-point function, but just the lensing effect in the 2-point function. Famously, Planck had a slight deviation here at about 2.5 sigma away from the expected canonical value of 1. So value of 1 just means that there's as much lensing as you would expect there to be in the given model. This is all within the context of Lambda-CDM. With ACT, we don't see any evidence of that anomaly. So the light blue curve here is the ACT DR6 result, which is centered right on 1. The different TT, TE, EE all give consistent results. We can combine with WMAP to get a tighter bound, which is shown in red here. And in all cases, we just aren't seeing evidence of this anomaly. So it looks that this is mostly probably significant evidence that what was seen in Planck was a statistical fluctuation. All right, so then let's turn to some more physical models of beyond Lambda-CDM cosmologies. And this is just a small sampling of what we did in this very lengthy paper. I encourage you to look there and see if your favorite model has been investigated. So let me first start with the primordial power spectrum. So this is really just in the context of Lambda-CDM at first. So for the first time, we can form a Planck-independent CMB data set from WMAP plus ACT that has similar error bar on NS, the scalar spectral index, to what Planck can achieve. And you see that we obtain a very consistent results and detect a deviation from scale invariance at about 7 sigma. So you can then make an inflationary zoo plot with ns on the x-axis and r, the tensor to scalar ratio, on the y-axis. The constraints on r here come from bicep plus Planck. With ACT, we don't measure those very large angular scales. But we sharpen up the constraint on ns considerably, as you can see here on the x-axis. One interesting fact is that ns moves up by about 2 sigma compared to the Planck result in orange. The purple here is p-act lb. Roughly 1 sigma of that comes from ACT, and about 1 sigma of it comes from the DESI BAO results. So the covariance between omega m and ns manifests in this shift upward by about another sigma. So that puts a little bit of pressure on the R-squared Starobinski model of inflation, which is shown down here, and generally moves us back towards effectively a linear shape of monomial potential. I wouldn't overinterpret this. These are 2 sigma bounds, so it's not like anything here is firmly ruled out, but perhaps an interesting feature. Okay, so then let's extend the model and look at running of the scalar spectral index. So this is allowing for some deviation from the power law form of the curvature perturbation power spectrum. We don't detect running. Here's our bound, slightly above 0, but consistent with 0. This is about a 30% improvement than upon the previous CMB plus large-scale structure constraints. There have been a sort of 3 sigma hint of negative running from Lyman alpha force data a couple of years ago, which this bound excludes at about 3 sigma. So we aren't seeing that that hint be confirmed here. Good, and you can see it's very consistent with the power law, which is the dashed black line in this this graph. So we do have a variety of other explorations of primordial physics, which I'll point you to in the paper. One thing that I'll highlight is that we looked for the first time in ACT data at the possibility of isocurvature modes. ACT allows us to tighten up small-scale isocurvature modes quite a bit beyond Planck, and we don't detect any deviations from adiabaticity there. All right, so let me move to later in the history of the universe. So one of the benchmark parameters for current and upcoming CMB experiments is n effective, the effective number of light relativistic species at recombination. So for the first time, we're able to push this bound significantly below the error bars from Planck. So this is about a 1.6, factor 1.6 improvement in the error bar upon the previous bound. Here are the posteriors with the previous data in orange, and then p-act lb, our new result, in purple. So one curious feature you can see is that it's centered a little bit below 3. And we did explore some possibilities for this. It's not statistically significant, but perhaps a curiosity for the future. If you combine with BBN data, assuming n effective is the same at the 2 epochs, then this sharpens up by another 20% or so. So these bounds then allow us to rule out the existence of additional dark radiation beyond the standard model neutrinos. So the graph on the right here shows a similar analysis, but where we now assume that the 3 standard model neutrinos exist and then look for excess dark radiation beyond that in terms of delta n effective. And these bands then show the exclusion on different from different data sets as a function of the decoupling temperature of the additional dark radiation particles, and for different types of particles, ranging from scalars to spin 3/2 particles. So with ACT-DR6, we can actually lower this bound enough that we exclude any spin 3/2 particle that was in thermal contact at any time after the QCD phase transition. So that's a first in these types of analyses. And of course, with upcoming data, we hope to push these bounds further down and eventually get the whole way back to reheating. Okay, I won't say too much about neutrino mass because the new DR6 primary CMB data don't change the story too much there. The lensing data and the DESI data really drive current constraints on neutrino mass, but our upper limit is down here at about 0.08 electron volts. All right, let me now turn to some models that change the dynamics of the universe around the recombination epoch, some of these motivated by the Hubble tension. So first, early dark energy. We studied this axion-like early dark energy model that's been quite popular in recent years in the H-naught context. So the potential takes this type of form, 1 minus cosine of phi, but raised to a higher power n. So n equals 1 would be an axion for various phenomenological reasons. that is really not a viable model for uh, increasing H naught from the CMB, so we fixed n to either 2 or 3 in this analysis. And here's what the potential looks like. So to parameterize the model, we used an approach that's become common in the literature, where instead of using parameters that are in this scalar field potential, we instead use some effective parameters motivated by this plot, which shows the fractional contribution of the EDE field to the cosmic energy budget. This is just for some particular example model. So the peak of this graph, of this curve really, we call FEDE, and that's reached at a critical redshift ZC. And then the final additional parameter is the initial position of the field on its potential, theta I. So this is a 3-parameter extension of Lambda-CDM. So in one slide, then here's what we found. So we do not see clear evidence of this component in the ACT-DR6 data. You can see the Bayesian posteriors here in this plot. FEE is down here on the bottom right. And you can see that for these various data set combinations, they all peak right at 0. Accordingly, this then limits the ability of the model to get a higher value of H naught. We had seen a hint of this at about 2.5 sigma in the DR4 data, our previous data release from ACT. It appears that this was consistent with a statistical fluctuation, and there's some investigation of this in one of the appendices of our paper. The New York Times summarized this, but we rule out this EDE idea. I'm not sure that it's completely ruled out, but certainly, as you could see looking at some of these plots, we're starting to really squeeze down the parameter space here and perhaps make it look a bit more fine-tuned. If you're concerned about using Bayesian statistics in this context, which there's been lots of debate about in the literature, you can instead do a frequentist analysis and just say, what is the delta chi-squared for the best fit EDE model compared to the best fit Lambda-CDM model? And scanning across all the data set combinations we looked at, the maximum we found when doing that exercise was a delta chi-squared of 6.6. And you can translate that with Wilks's theorem into a Gaussian sigma of about 1.7 sigma. So it's not a significant improvement, and we don't see any meaningful hint of this component. Okay, so then let me turn to a different type of model, also motivated to some extent by H naught, in which you modify the dynamics of recombination somehow. So there's many ways to do this more physically, for example, with primordial magnetic fields, allowing the fundamental constants of nature to vary, or changing the properties of the CMB monopole. Here, we studied all of these in the paper, I should say, so you can find the constraints on those in our paper. But here, let me show you the results of a more model-independent approach to this. So what we do is you perform a non-parametric reconstruction of the ionization fraction during the recombination epoch. So what I'm showing you in this plot are basically a reconstructed spline from pre-ACT data on top in orange, and then the new data including ACT on the bottom in purple. And what you can see is that the error bars really tighten up with the inclusion of ACT, in particular at the high redshift beginning of recombination, corresponding to smaller angular scales, which we probe better with ACT. And then also you could see that the purple contours here are very nicely consistent with the standard recombination history in the dashed black curve. So we're not seeing any deviation at the moment from standard recombination physics. That then accordingly restricts the ability of such scenarios to increase the value of H naught. So this is the resulting marginalized constraint on H naught in these models. When you add the ACT data, you go from the orange to the purple, so it moves you back down towards the standard model. There is some dependence here on what BAO data set you use. There's an interesting covariance with the value of omega m. So the dash curves here use BOSS instead of DESI, and you can see that that does lead to a more Lambda-CDM-like result. But in all cases here, there's no significant deviation that's seen. Okay, so I'm just scratching the surface of what we did in this paper, but I'll summarize the picture for H naught here in this slide. So this is a whisker plot that shows the constraints on H naught, first in Lambda-CDM up here in black, and then from a variety of extended models in all these other colored points. So what you should see is that, first of all, in all cases, we never see a shift that's larger than about a sigma. And we don't detect any of these extended models in any case. If we had, I would have already told you about it earlier in the talk. And what this means then is that the tightest limits the date on a wide range of beyond standard model scenarios that are captured in these different points here. The other implication, of course, is that if you compare to the shoes measurement of H naught, which is shown in gray, there's significant discordance. So Lambda-CDM, of course, was already very discordant, but even in these extended models, we don't see any particular instance in which H naught moves up to be concordant with shoes. So we looked at a very wide range of models. Of course, there's no theorem that there's not a clever model that hasn't yet been constructed. So um, perhaps back to the theory drawing board. The CCHP H naught result is here in yellow, and you can see that it's broadly concordant within the error bars, already with Lambda-CDM in our analysis. Okay, so then let me turn to S8 quickly. So we looked also at a variety of models that could potentially have decreased S8, the late time fluctuation amplitude. So this is a plot that summarizes a few of those models with S8 on the x-axis and then some new physics parameter on the y-axis. The Lambda-CDM results are shown in this purple band from P-ACT-LB, and then the DES plus KIDS constraint that was in the literature prior to our result is here in yellow. KIDS subsequently released an updated measurement, which is probably being discussed at this conference, which moves their result up higher, such that in Lambda-CDM everything really looks pretty much concordant. We didn't see evidence of any of these extensions that could have lowered S8. So at the moment, this tension sort of seems like it's perhaps looking less significant. Okay, so in the final chunk of time here, let me perhaps tell you about any curiosities that there might be that could motivate where to look in the future. For example, I told you we looked at about 30 models. So just from the look elsewhere effect, they should at least see 1.5 sigma hint. And if not, then the error bars must have been overestimated. But there's a couple of things that fluctuate into maybe an interesting result. So let me first start with looking at this scenario in which the growth of structure is modified. So this is a model where the growth rate, so d log d by d log a, where d is the growth factor, is parametrized in this form as omega m to the gamma, where gamma is now a free parameter. So in general relativity, gamma has a canonical value of 0.55, but we can open up that parameter and see if data prefer a deviation. So the plot on the left that I'm showing you here is an end-to-end test, like the one I showed you earlier for CMB lensing and for BAO, where you take the best fit Lambda-CDM model to the CMB data and then predict F sigma 8 as a function of redshift. So that's what the shaded bands are. And then the different points are measurements of F sigma 8 from redshift space distortions or from peculiar velocity surveys. So broadly speaking, things are pretty concordant, but there's two outlying points at very low redshifts here from peculiar velocity surveys that exhibit a discordance. So the chi-squared is actually not good. But if you throw those out, then the chi-squared becomes okay. So it's a little bit unclear what's happening. If you do a joint fit to all the data, then the inferred value of gamma is given down here at 0.63. So it's about 3.5 sigma higher than the GR value. You could also do the fit without using the F sigma 8 data. So that's the P-ACT-LB purple contours in this plot on the right. And you can see if you look in the gamma panel that now it's consistent about 2 sigma with the GR value, but it is still a little bit high. One curious fact, this has been seen in earlier work from Min Wen, Dragon Hooterer, and others. One curious fact, though, is that now with the ACT-DR6 data, we can exclude the lensing anomaly of Planck as being responsible for this gamma feature, because the P-ACT combination really doesn't show a lensing anomaly, and this still peaks a little bit above 0.55. So it's not at all clear what's going on. Really, if there is a deviation, it's driven predominantly by these two peculiar velocity survey points. But given recent hits from DESI of dark energy perhaps behaving strangely at low redshifts, it could be a sign of a place to look in the future for some independent evidence of something new going on. So I would call that just a curiosity for now. I can't finish the talk without telling you something about dark energy. So here's the state of affairs as of mid-March when we posted our papers, the day before the DESI DR2 results came out. So the primary CMB doesn't really weigh in too much on time-evolving dark energy, except insofar as the value of omega m can become more or less concordant with that measured at late time. So the P-ACT value of omega m is in a bit better agreement with DESI than Planck alone. So if you do a joint fit, including ACT, then it with DESI DR1 becomes consistent with lambda at 2.2 sigma. And of course, if you use BOSS instead of DESI, you get the green contours, which are very consistent with lambda. Um, as you all surely know, DESI DR2 came out the next day. And so we've done some internal analyses, taking a look at the interaction between ACT and PACT and DESI DR2. So here's one of those. So this is now looking at this end-to-end test of the model where you take the Lambda-CDM fit to the CMB and then predict the distance redshift relation and see how it compares to the BAO results. And what you can see is that the p-act curve, which is the dark dashed blue curve here, agrees quite well with the DESI DR2 data points. The PTE value is 13%, so that's actually even better than DR1. Planck alone famously is discrepant with a 1% PTE, and it all comes down to the best fit value of omega m, which for p-act is a little bit lower than the one from Planck alone. So you can then translate this into constraints on W naught WA if you run the fits. There's a paper from DESI doing some of this. In our own fits with PACT plus SEDR2, it's something like 2.4 sigma if you say preference over a Lambda-CDM. So I would still file it under a curiosity, but definitely an interesting place to see how things proceed in the next few years. Okay, so I'll summarize then. So this is a nice plot from Louis et al. Summarizing the state of affairs in CMB cosmology at the moment. So the new ACT-DR6 data points are here in red, extending in particular the E-mode power spectrum out to small scales for the first time. The Planck results are in light blue. We're all excited to see the upcoming SPT results, which should provide an interesting independent test of some of these results that we recently found with ACT-DR6. So to summarize, we've really tested the cosmological model in a totally new regime with the ACT-DR6 measurements, particularly in polarization. I think it's remarkable that Lambda-CDM continues to succeed in a new domain like this. We looked at a huge range of BSM scenarios in our work and didn't detect any of them. Accordingly, that means that we put the tightest constraints on a wide range of those scenarios to date. This, of course, is not the end of the story. So at our site on Cerro Toco in Chile, we've been constructing the Simons Observatory. Here's a little video showing the primary mirror being put into the Large Aperture Telescope. That is now operational, and we've been taking data already with the LAT and also with some of these small aperture telescopes targeting primordial gravitational waves. So it's going to be an exciting decade coming up for the CMB with much higher sensitivity to new physics even than what we've achieved here. So I'll stop there, and I will leave it to Armenia to answer your questions about this work at the conference, as well as Thibaut. So thanks a lot.